So here I'm explaining the mathematical preliminaries. So before we dive into probability, let's quickly review some foundational mathematical concepts that will be essential. We'll be working with sets, sequences, and series. So a solid understanding of these basics will make our journey smoother. So here are the equations for mathematical preliminaries. So for example, in the set union, so A cap B slash X and mid X in A and X or X in B. In the set intersection, it's A cap B equals E slash X, E slash mid, and X slash in A X and X in B slash. Then set complement AC equals 1X slash mid X slash not in A slash X and X slash in slash omega. So here I am explaining or discussing about the sample space for defining possible outcomes. So the very first step in building any probability model is to define our sample space. So this is the set of all possible outcomes of a random experiment. It's crucial that the outcomes listed in our in our sample space are both mutually exclusive. Only one can happen at a time and collectively exhaustive. The sample space covers every possible result. So here are the equation for sample space. So sample space slash omega equals slash E, then underscore 1, E underscore 2, E underscore 3, and slash dots. So for a single coin flip, in omega or slash omega equals slash curly brackets text, curly brackets heads and tails, and curly brackets and slash and curly brackets. So here are the assigning probabilities and the axioms. So once we've defined our sample space, the next critical step is to assign probabilities. For continuous spaces, we assign probabilities to subsets of the sample space, called events. So these probability assignments must adhere to three fundamental rules, known as the axioms of probability. So here are the equations for axioms of probability. Number 1 is probability of an event. So read this. And axiom 1, non-negativity. Axiom 2, total probability. And lastly, axiom 3, finite additivity. So here I will discussing 5 and 6 of properties of probability. So from these three basic axioms, we can logically derive many other intuitive and useful properties of probability. So this help us calculate probabilities in more complex scenarios. So these are the examples of equations for properties of probability. So here I'm discussing now about the discrete uniform law, the seventh topic. So a very common and straightforward probability law applies when all outcomes in a finite discrete sample space are equally likely. This is called the discrete uniform law. So here are the equations for discrete uniform law. So now I'm discussing about continuous uniform law. So this is similar to the discrete uniform law, but it is a continuous uniform law. Applies to continuous sample spaces where probability is proportional to size, often area or length. We'll use the dart example to illustrate. So here are the equation for continuous uniform law. For example, it is a dart on unit square. So now I'm discussing about countable additivity. So when dealing with infinite discrete sample spaces, we need a stronger version of the additivity axiom called countable additivity. So this allows us to sum an infinite series of probabilities. So here are the equation for countable additivity. So I'm discussing about what is probability. So beyond the mathematical framework, it's important to understand the different interpretations of probability. Is it about what will happen in the future or what we believe will happen? So both views are valuable. So here are the conceptual representation for probability interpretation. sum is the frequency and computation.